Hello. Welcome to integrating Redis Streams as custom resource definitions within Kubernetes. Before we begin, let's set some expectations. This is an architectural talk and not a tutorial on how to build a full-fledged application. You can apply these principles to any Redis resource and any other third-party tool, but the focus of this should be on how to explore how to use this within an actual business. I've been using Redis to power my applications for the last 10 years or so, and it's become a staple component of my designs. Though quite a bit newer, Kubernetes has similarly taken a place as a basic tool, and in fact, I run most of my Redis clusters on top of Kubernetes. I recognize they both serve different purposes, obviously, and I wouldn't have thought to integrate the two had I not read in the Kubernetes documentation that if you wanted proper, fine-grained job handling, you likely need to implement something along the lines of a Redis-backed queuing system like ResQ. When I read this, I thought, hang on, wait a second. Why can't I do this in Kubernetes? And then I realized it was designed more for cron jobs than background jobs. So I started writing a prototype to link the two together and use the best of both worlds. I thought it was interesting enough to submit a talk proposal and was honored to be accepted. Hopefully I'll do it justice. My name is Christopher Kliga, and I'm a software engineer, among other things, from London, England. As I said earlier, I'm a Redis fan and a big proponent of event-driven architectures and asynchronous processing. So during this talk, we're going to look at Redis Streams and Kubernetes and how they might help in running a fictitious coffee shop, where orders are constantly stacking up, systems need to be made more efficient, and management needs a view of what's going on. So let's imagine we have a coffee shop in San Francisco. We can't be there in RedisConf, but at least we can be there in spirit. Unfortunately, we're a victim of our own success. Our coffee shop is so great that everybody wants a piece, and we don't have enough baristas or machines to handle the orders. As a result, we have to close down. Fundamentally, we have two problems. The first, how do we make this more efficient so that we don't break when we get a bit overloaded? The second is, how does management get a view so that we can take necessary actions to scale up and down accordingly? Come on, we're all tech people here, so clearly there has to be some form of tech solution that we can use to fix this. And let's be honest, it'd be a pretty boring talk if I said, let's use pen and paper. So for the first problem, obviously, we're going to talk about queuing and the ability to deal with jobs in a priority basis. Redis is good for that, so let's use Redis. The second problem effectively involves a management layer. And while we could build a web application to run it, I tend to think of Redis Streams and other Redis resources as basically infrastructure components, more than application components. So if we leverage the best of both worlds, that is the queuing capabilities of Redis and the resource management of Kubernetes, then we should be able to come up with a solution that solves both problems. But obviously it's not that simple. We can't just throw tech at the problem and expect it to solve everything. That'd be way too easy. So we need to figure out how to integrate the two in a way that feels native to both developers and managers, and without too much cognitive overhead for either. In order to do that, we'll have to review Kubernetes basics and the nature of custom resource definitions. Then we look at Redis streams and how they work. Once we've got those under our belt, we can figure out how to go about putting them together in a custom resource definition, and then proceed to look at architecting a resource controller for our new CRDs. Once we have these things sorted out, we should be able to fix the problems in our coffee shop and get back on track. So for those of you who might not know, Kubernetes is an orchestration and scheduling platform for containerized environments. It's kind of like the store manager in a coffee shop, always making sure things are working efficiently and as expected, and fixing things that go wrong along the way. Containers provide a relatively standardized format for packaging and deploying applications. Yes, I believe that was Java's promise as well, but that's neither here nor there. The more real-world example would be a coffee cup. The shape is the same, and it doesn't really care whether it's got coffee in it or hot chocolate or tea. It's all pretty standardized. So they exist in relative isolation, interacting with the host with little to no knowledge of what's actually happening on the machine. And as you can imagine, they get a little bit chaotic in their isolation. I don't know about you guys, but COVID-19, I feel a little chaotic. Kubernetes helps manage some of that chaos by organizing resources and setting constraints appropriately. It makes sure that things get resolved and that issues get resolved, I should say, and that resources aren't being squandered by zombie processes. It does this by using effectively something called a spec, a specification, which defines the configuration of the resource. If you've ever had a latte or cappuccino, you have a basic idea of what a spec looks like. Even though they're the same resources or the same ingredients, they're put together a little bit differently, and they come out with different things. A spec is fundamentally a data blob, usually in the form of a YAML or JSON definition, which defines the type of resource, called its kind, its version, its name, and its namespace appropriately. Speaking of namespaces, resources can either be constrained or to a namespace, or can be cluster-wide. So what that means is namespaces allow multiple tenancy, so you can run the same resource with the same name within different namespaces. Resources are effectively defined as either being native or custom, non-native resources. So basically, it's broken down to what ships with Kubernetes and what you add after the fact. Admittedly, custom resources are the primary means of extending functionality within Kubernetes. And they're based on custom resource definitions, which act as models or templates for resources. If you've ever done any object-oriented programming, then you understand the difference between a class and an instance. That's the closest analogy I can come up with for this. With regards to the real world, a recipe for coffee is a good example of a custom resource definition, while the resource itself is represented by something like the latte, which will be configured with milk, sizes, portions, so on and so forth. CRDs define a set of rules for how they're instantiated, kind of like that recipe example, and can contain data validation so that we guarantee that information that's needed is provided in a predefined format. Custom resources on their own are purely data objects. They describe the fact that a resource exists and maintain some bit of information about its state. An order for coffee is a good example here. It defines that the order exists and that it has a unique order number. It contains what's in the order, but not necessarily the definition of, isn't the order itself, isn't the coffee itself. So the actual making of the coffee falls to the barista, or in Kubernetes parlance, the controller. The business logic is this thing that we're talking about, and controllers hold that, which allow them to manage and interact with the resource in question. Just like a barista knows how to use a machine and produce those delicious drinks, we hope, a controller interacts with some piece of software or hardware to produce or manage the resource. Controllers implement APIs or expose APIs, which is the means by which Kubernetes interacts with them. Those APIs provide a basis for common language and understanding between the client and the controller. The understanding has to be there or translated appropriately, otherwise they have no idea how to work together. It's the difference between asking for a tall, grande, or venti in a Starbucks, or just a small, medium, or large in a regular coffee shop. Controllers require programming. Resources do not. As I said, because the controller applies logic and the resource is just a data definition, therein lies the difference. So an example of a custom resource definition would be something like this. It contains the kind, API version, spec, and the relevant configuration information for the Kubernetes API to actually accept this. Or something perhaps a little more coffee-oriented would be a type called kind. This would allow us to instantiate coffee resources in our cluster. So to review, we can define coffee as a custom resource within our cluster, or streams within our cluster. The actual type of coffee is defined by a spec, and that is to say, the actual custom resource instantiation. A CRD is like a recipe or a model. It's data only, and the actual making of the coffee or the instantiation of the resource is handled by the controller. So, given that we know how Kubernetes can help us, the question is, what about Redis Streams? A stream is a time series data store. Each record gets a unique timestamped ID based on when it was received. In our case, that might be an order, for example, with the timestamp indicating the order ID or the priority in the queue. The stream is append only, so we can obviously read from it, but we can't modify records once they're in the stream. Orders in our coffee shop can be read in either a blocking or non-blocking fashion. So in the case of our baristas, that means that we can have some pretty efficient ones who are just waiting to get going, or we can have ones that check back every so often while they do other things. Messages, or in our case, orders, are created as maps of key value pairs, which define when the message is, when the message is added to the stream. This would indicate different types of data, potentially for different consumers, and which is how messages get processed. Consumers can request messages either individually or in ranges. As each message is timestamped, that they would use that as the ID, or they can say, give me the messages that started from here to there, the last time I checked in, for example. Unlike lists, messages can be read by multiple consumers within a stream. And now this is useful for multiple purposes, one of which is different types of consumers processing the same piece of information differently. Consumers may share an affiliation based on role, for example, and form consumer groups. So to go back to our example of baristas, baristas may form together in a group so that each individual barista self-identifies, and messages can only be handled by one barista at a time. This allows consumers to reserve messages based on that ID, so that if they accidentally disconnect, or if they disconnect for a reason because it takes a while to process the message, they can then reconnect and instantiate their reservation. As consumer groups track read and unread status of each message, you're guaranteed that each message is only passed to one consumer at a given time. And messages need to be explicitly acknowledged and removed acknowledged as completed to be removed from the consumer group. So again, they're not accidentally processed or reprocessed by multiple consumers. So to recap this, a stream is an append-only time series data store. Messages are just a data map, and consumers can belong to a consumer group which tracks the read status of the message. So in order to remove it, it has to be explicitly acknowledged. Now this is really, really useful for any kind of queuing operation, because it means we can have multiple queues, that is to say multiple streams, and multiple workers within that in that queue, or in that stream, multiple queues, so the stream, and multiple consumer groups, which is different types of processors. So we can have multiple workers within that process dealing with these streams and dealing with these jobs as we go. So given that, we know how CRDs and Redis Streams work, so let's look at how we put them together. If we define a basic CRD called a stream, this is what it would look like. We're not specifying any kind of validation rules on the stream, mostly because I couldn't fit it on the slide, to be honest, but you can indeed specify validation rules. When I do eventually upload this to a public location, I'll put the code up there so you can access it and see what I mean. If we created this a CRD, we might create a new stream called coffee orders, for example. In this case, we've defined a schema. The schema is not a required field. It's the name of the key value pair I've specified. And if we go to look for it, if we ask Kubernetes to give it to us, this is what it would give us, this list of coffee orders, or this stream, I should say. But that's not really helpful. So let's add some additional fields. If we were actually creating a stream, we might want something like message count or unread messages. We'd want to be able to track information about that stream when we ask for it. And so we'd get that information as we request that stream information. We'd say we have a coffee orders with a message count and an unread count. However, there's missing data, and the question would be why? Well, obviously, it's because custom resources are data only. In order to get that data, we would need a controller. And that's what we're going to look at next. So we've come through. We've got the review. We've got the Kubernetes controller. We've got the stream. We've got a CRD. Or sorry, we don't have a Kubernetes controller. We're looking at building a Kubernetes controller. We've got an understanding of the streams. We've got an understanding of the CRDs. If we were going to build a controller, what would it look like? So just so we're clear, we're not actually building a controller in this talk. I will do a follow-up talk on building a controller in Redis, for Redis Streams in Golang. If you want to build a controller in the short term or in the immediate future, I highly recommend Programming Kubernetes by Michael Hausenblas. It's a good introduction to how custom resources work, operators, controllers, the like. So controllers are the thing that manage resources within Kubernetes. It exposes APIs, allowing you to control the resources within its purview through it, obviously. And it provides a means of discovery, so you don't actually have to know what it looks like in advance. That's actually one of the best things about Kubernetes in that regard, is the ability to explore resources accordingly. Resources can either be managed imperatively or declaratively. Imperative management means that you say something like, I want a latte. Declarative management basically says, make coffee, heat the milk to this thing, mix it this way, X, Y, and Z. It's the steps in the process to get there. Kubernetes predominantly uses an imperative definition through YAML and JSON specs. So operators are the controller interface for a specialized resource. And in our case, that would be Redis or Redis Streams. All operators are controllers, but not all controllers are necessarily operators. That specialization makes a difference. Now, controllers run a reconciliation loop, which verifies the state of the resources. So if I was saying I wanted a resource, like a Redis stream, for example, it might go and instantiate the stream by pushing a first initial message. Or if I wanted something like 10 instances of a given application running, or a worker, it would go and say, oh, I only have 5 running at the moment, let me add an additional 5. So it runs this consistently over and over again, just to make sure that it keeps the desired state, the user-declared state, into the actual reality of the situation. And if we're going to do this with a Redis Streams or Redis operator, Redis controller, we would need to integrate the SDK. That's the means by which we would actually interface with our Redis cluster. And then we can reconcile our streams. So you can say, create the stream, delete it, query it, give me information about it. And then we can manage it and actually get that list of information, thereby allowing us to act accordingly. Now, there are different types of information we might want to get. Some of it might be just simple stuff as give me the list of streams. Some of it might be very detailed, in which case we could use things like describe to actually manage that and get logging information. There's lots of things we could do if we really wanted to. So once we had that, we would be able to actually solve this theoretical problem. And we'd be able to go back and solve the 2 issues that we had. The first one being, how do we make this more efficient so we don't get overwhelmed? And the second one being, how do we manage it once we have? We're almost done, I swear. I promise you can go get a coffee after this. But we have 2 solutions to these problems, right? For the first problem, with regards to the overwhelm, well, we're using queues, and we're using Redis streams and consumer groups to deal with that now. For the second problem, where we have where we're asking about how do we manage it, well, we manage all sorts of other infrastructure and other bits and pieces, and often enough we'll use Kubernetes to do that. So we might as well use the same approach to manage our streams and our Redis resources. Thereby we can leverage additional Kubernetes tooling, logging, management, and auditing tools, and so on and so forth. So doing that, we managed to solve the problem. I've solved my problem, at least. I got a cup of coffee that admittedly I had to make myself. And the app to do it isn't quite working yet. It's still a work in progress. And when I actually wanted to screenshot it so I could show it to you guys, it failed miserably. But that's not really the point. The point is you can integrate Redis streams and custom resource definitions with Kubernetes. And actually this whole approach will apply for any resource stream. Or any Redis resource, I should say. More than that, you actually should integrate the two, because if you're actually going to be building on Redis, you want to start treating your Redis resources, as infrastructure. You may have to blow them away. You want to be able to create them as and when is needed, and you may want to scale up accordingly just to be able to put them in place. So in fact, I've been looking at replacing etc. D or etcd with Redis as the basic Kubernetes. In fact, I've already started work on it. I think if we can do that, there's a lot of functionality within Redis that would allow us to do things like eventing, pub/sub notifications, the various different data forms in Redis. We'd be able to do a lot of things with it that you can't do natively from etcd. But that's a topic for another conversation, or another talk, I should say. I will do it at some point, so look for the follow-up on this. And in the meantime, give me a shout if you've got something interesting to work on. I've just finished up a gig, so I'm looking for something new to do and some fun next adventures. Reach out to me if you've got something you think might be up my alley. And as we're at the end, thanks for watching, and if you have questions, please reach out through the various forms, and we'll talk in the future. Have a good one.